Hi, I'm Professor Melko, Chemistry PhD, and today we're going to take a look at models of the atom, from Dalton, Thomson, to Rutherford, and discuss some atomic notation. Let's jump into the lecture. So here I've listed sort of the different models of the atom that we'll cover in this lecture and the next lecture. For this lecture, we'll start with Dalton, go through Thomson and the Rutherford atom. Next lecture, we'll get into the Bohr model of the atom and the quantum mechanical model, which is sort of our current model. So moving from left to right here, they're getting more accurate, but also more complex. To start with the Dalton model, here's Dalton up in the upper left here. He proposed that all matter was made up of tiny particles. So he was really the first to outline this hypothesis that everything can sort of be divided up into this small, tiny particle called an atom. Thomson then went, here's Thomson on the right, Thomson went and took this a step further, saying these tiny little particles called atoms are actually composed of something a little more fundamental. You have these charged particles called protons, which hold a positive charge, and sometimes we'll see them symbolized as a lowercase p. Okay, and these protons have a +1 charge, symbolized by p+. And you also have these negative charges called electrons. These are symbolized a lot of times with a lowercase e with a negative sign. So each proton has a +1 charge, each electron has a -1 charge, and those charges kind of balance each other out to make the overall atom neutral. Of course, you can remove or add electrons to change the overall charge on the atom. So Thomson proposed that, but he also incorrectly proposed a picture of what that atom might look like. And he said the atom is this spherical tiny particle, which is correct. But he said there were these spheres of electrons, these negative charges, that I'm going to symbolize here with little negative signs, that were distributed throughout this background sort of positive smear of positive charge. Okay, that's why it's called the plum pudding model, this sort of cake where you have this uniform, consistent, in this analogy, positive charge with these little plums throughout, where the plums would be these local pockets of negative charge. So that was sort of the working model at the beginning. After Dalton, Thomson came up with this model. Some of it was correct. We have protons and electrons, but they're not distributed in this manner. And really, it took an elegant experiment to find out that they're, in fact, not distributed like this, but distributed in something called a nucleus. And that's the Rutherford model of the atom. So Rutherford was the first to propose this atomic nucleus, right? That we have this really dense area, and then surrounding that, there might be some electrons, perhaps in orbits, perhaps just further out. So the electrons are somewhere out here, distributed around this positive nucleus. Okay, so Thomson said it was this positive smeared out charge. Rutherford said it's this dense central nucleus. Okay, Thomson said the electrons were these small pockets of negative charge. Rutherford said, no, these are distributed around this positive nucleus. They're not just sort of everywhere throughout the positive charge, but they're distributed around this central nucleus of positive charge. Rutherford, importantly, also made this hypothesis that the nucleus contains some neutral particles. And these we'll discover later. I'll just write for now N0 for neutron. Those are the neutral particles, in addition to protons that are found in this nucleus. So the experiment that really let Rutherford hypothesize these characteristics was the gold foil experiment, one of my favorite experiments in all of chemistry. Rutherford had his student fire alpha particles at thin gold foils. Okay, and the story goes that Rutherford didn't expect much of this, thought it would be a really quick experiment. He kind of expected the alpha particles to go right through the foil. And the reason is because these alpha particles are really, really energetic. Okay, so these alpha particles have high energy, and it'd be equivalent to you shooting a gun at a piece of tissue paper. That's kind of what they thought at the time. But instead, when they ran this experiment, all of the bullets didn't go through the tissue paper. Some of them bounced back, right? And they can only bounce back if they were ricocheting off something super dense, right? So if the Thomson model was correct, the foil would an analogy, be like tissue paper. The bullets would go right through. But they bounced back, which led Rutherford to propose his model of the atom in the lower left here, where you have this dense nucleus. So there has to be some really dense charge that these high energy particles can ricochet off of. Right, so that's what's summarized here. If the plum pudding model of the atom was correct, the particles passed through. However, some of the alpha particles were deflected backward. Okay, and that's really what led Rutherford to propose this dense central nucleus. So there's a little animation here. This is a PhET, P-H-E-T, if you want to look it up, Rutherford PhET, where it's just kind of like a little animation that you can play around with. We'll fire alpha particles here, these small purple dots. You can see the orbits, or these dashed lines, around these central yellow nuclei. And you'll see some of the bullets are getting ricocheted at really sharp angles, and some of them will even be sent back down towards where they were coming from, towards the bottom of the screen. Right? Plum pudding would look something like this, and the particles would all just pass directly through. Okay, so those are the various models of the atom we're going to start with. Once we had this Rutherford model, we began to come up with something known as atomic notation. Okay, we now know this nucleus contains protons and neutrons, and there's electrons sort of surrounding that. So as chemists, we want to signify that with some shorthand. And the shorthand we're going to use is atomic notation. Okay, that's what's shown at the bottom of the screen here. I'll write it up here again, a little cleaner. This is atomic notation for a carbon atom with 6 protons, 6 neutrons. Okay, so how this is laid out is the atomic number, the number of protons, is this lower subscript to the left of the element symbol. So if it's a carbon atom, I write the symbol capital C. To the lower left of that, I write 6 because every atom of carbon has exactly 6 protons. Okay, that's the atomic number. We sometimes abbreviate that Z. Total number of protons plus neutrons is the mass number. That's abbreviated A. Okay, and this mass number is the superscript before the symbol. Okay, so this mass number is always going to be greater or equal to this bottom number, because it's protons plus neutrons. Bottom number is just protons, the upper number is protons plus neutrons. So here, the carbon atom has 6 protons, we know that for sure. 12 minus 6 is 6, so it has 6 neutrons. Again, our symbol here is written in capital letter and lowercase letter if there's a second letter in the symbol. The atomic number, lower left, mass number, upper left. Atomic notation displays the number of protons and neutrons in the atom. Okay, so that's what we're after. So here's the example again, sort of laid out. For carbon, Z equals 6. That's the atomic number. A equals 12. That goes in the upper left. The number of neutrons is then the difference in these two numbers. Okay, so if you're given these sort of atomic notations and asked for the neutrons, you always subtract those two numbers. For neutral carbon atoms, the number of electrons is 6. Okay, so as long as the atom is neutral, the positive charges, right, protons are the positive charges, must equal the negative charges if it's a neutral atom. So if we see that this carbon atom has 6 protons, then we automatically know there's 6 electrons if it's neutral. Isotopes are atoms of the same element, so they have the same number of protons, but they have different numbers of neutrons. Okay. Every single atom of carbon has 6 protons. The number of protons is what makes that element, but they can have different numbers of electrons. Okay, so we could have they could have different numbers of neutrons. That's an isotope. So here's carbon. Carbon always has 6 protons, so this atomic number is always 6 for carbon. But this upper number, in the previous example, we wrote a 12, but you could also have an extra neutron. So on the left, I have 6 neutrons. On the right, I have 7 neutrons. They're still both atoms of carbon because they both have 6 protons. That's what makes them carbon. But the one on the right has 1 extra neutron. So these atoms that have different numbers of neutrons but the same number of protons, we call these isotopes. So these are isotopes of carbon. You may have heard of carbon-13, used for carbon dating. That is an isotope of carbon. So these two different isotopes will always have the same atomic number of protons, but different mass numbers because their neutrons are different. So let's take a quick moment here to practice a problem. You can pause the video now and try to answer the following question. I'll work through it in another second. So the first one, atomic number. So here we want atomic number, mass number, number of protons, number of neutrons, number of electrons. Okay, so remember the atomic number here is to the lower left. That is 4. That also represents the number of protons. The mass number upper left, 9. That is protons plus neutrons. So the number of neutrons here is always the difference between Z and A. Here that is 5. There are 5 neutrons plus 4 protons, make up the 9 total for the mass number. Assuming this is a neutral atom, the protons, that positive charge, always has to equal the negative charge. So whatever the protons are, there must be the same number of electrons. The second one here, phosphorus, Z is 15. That's also the number of protons, also the number of electrons, assuming this is neutral. 31 is my mass number. The difference between Z and A is my number of neutrons. Here, that's 16. So that's the atomic notation for beryllium and phosphorus in this example, and the number of protons, electrons, neutrons in each of these examples. Next, we have to discuss atomic mass units. Okay, we know these little tiny particles have mass, they are matter. Those masses are really, really small. Okay, so we use these small atomic mass units to describe that. The mass of a single atom is really small. Here's carbon, 1.99 times 10 to the negative 23 grams. Right, that's an awful lot to write out and keep track of, so instead scientists determine the mass of atoms sort of relative to each other. Okay, so rather than have these sort of funky numbers and really, really tiny numbers, we're going to sort of standardize all atoms to carbon-12. We're going to say carbon-12 weighs exactly 12 atomic mass units. Okay, so we've just changed from grams, where the number is really small and kind of weird looking, to something that's uniform. So we've gone from grams to atomic mass units. So we're just going to say the mass of carbon here is 12 AMU. And these AMUs is what you'll see listed in the periodic table. That's sort of where we're moving with this terminology. Now, on the periodic table, you will see weighted averages of the atomic mass. So remember we talked about isotopes of carbon, different numbers of neutrons. Those atoms then have different masses. And the mass you see on the periodic table accounts for those two different masses and weights them accordingly based on how much of one isotope versus another is present in nature. So it uses this concept of weighted averages. Simple averages we're really familiar with. You just sort of add up all the numbers and divide by the number of things, right? Weighted average takes into account that different objects may be present in different amounts, right? So then you multiply percentages by a certain value. Okay, so that's a weighted average, and that's what we use in determining the average atomic mass. Makes more sense if we look at an example. Okay, so this average atomic mass is a weighted average that accounts for the different isotopes. So just like before, we said we had carbon-12 and carbon-13, we can have gallium. So here's gallium-69 and gallium-71. Okay, the mass of gallium-69 is 68.926 AMU. So we're working in this unit of atomic mass units, not grams. Gallium-71 has a mass of 70.925 AMU. Now in nature, there's some gallium-69 and there's some gallium-71. And it's not a 50-50, it's not an equal ratio. Nature's not that simple, right? Instead, this gallium-69 is in 60.11% abundance. The rest then is gallium-71. So, on average, what is the mass of gallium? It's a weighted combination of these two masses, weighted particularly by their corresponding abundance. Okay, so to find the average atomic mass of gallium, we take this weighted average. Right? We take this mass of gallium times its percentage in decimal form, and add to it the other mass and its corresponding percentage. And you're going to get some number that's between these two because it's an average of those two. It's a weighted average, so it's not exactly 70. It's pulled a little closer to mass 69 because there's more 69 than there is 71. Okay, so here the weighted average gives us a value of 69.72 atomic mass units. So we can look on the periodic table. Here's gallium. Here's this 69.72 atomic mass units. Right, for carbon, it's 12.011. Okay, it's really close to 12, which tells us that most of the carbon probably is carbon-12 in the universe. But it's a little higher, so there's probably a little bit of this heavier version of carbon that's sort of pulling up this average away from just carbon-12. If it's 100% 12, then the average would also be 12. But the 13, there's a little bit of it. It pulls the mass a little bit higher. Okay, so on the periodic table, we have these average atomic masses. We also list, you'll see, these atomic numbers, right? These values we list to the lower left in our atomic notation are also found on the periodic table. Okay, the periodic table doesn't necessarily use atomic notation, but it does give us this atomic number and this average atomic mass units. Right, so that's what's shown here. The periodic table shows this atomic number, this symbol, and this atomic weight. That'll do it for today's lecture. We sort of introduced the different models of the atom and how to write atomic notation. Okay. Next time we'll get into more advanced models of the atom, including the Bohr model and the quantum mechanical model. As always, you can subscribe to this channel on YouTube for more videos like this and lectures. You can check out my office hours every week on Twitch, where I work practice problems, do review sessions for exams, and sometimes just talk about the latest science news. Catch you next time.